So here we go, part B, double replacement. So a double replacement, it's very similar to a single replacement, a little bit more complex, not too bad today. Section 8.3 is actually dealing with more of double replacement. But here's the general form, kind of like what we were dealing with yesterday. It could be any letters, and I'm using A's and X's and Y's and B's here, but it's AX plus BY goes to AY plus BX, as you can see. And what's happening is, depending on how you look at it, the A and the B are switching, or else the X and the Y, in this case, are switching. So two things are switching. It's very similar to single replacement. That would be more like A plus BX. So there's one thing in a compound reacting with a bigger compound would have went to AX plus B. So they're similar, okay? But the double is a little bit more complex. So how do you tell if you have a double replacement? You write out the reactants. It's going to be two ionic compounds. Okay? So reactants will be two ionic compounds, or acids, which are technically ionic compounds anyhow. So you have two things. They might have a metal at the beginning of both of them, or one of the two things might be an acid. Okay? So that's what double replacement is. That's how you tell. Remember, you need to be predicting products here. And then also another thing to watch for is usually they're in aqueous solution. They pretty much have to be dissolved in water, which again is the aqueous solution. So usually an aqueous solution. And it'll say that. It'll say a solution of, or dissolved in water, or aqueous forms, something like that. I'll give you a hint. And then we'll do a couple examples here. Anybody need that slide still, that last one? Fast. Okay. So a couple examples here. And again, we're going to be doing this in 8.3, so I'm going to just touch upon it a little bit today and a little bit in the homework, and then 8.3 will really get hard. So the first example, you have sodium hydroxide. That would be called reacting with iron 3 chloride, or FeCl3. So I'm giving you the formulas here. So what type of reaction? This is definitely a double replacement. You might want to write DR up somewhere. It is a double replacement. How do I know? Because I have an ionic compound right here reacting with an ionic compound right there. How do I know there's ionics? Because there's a metal in each of them is a pretty good indication to me. Metals bonded to non-metals. So what's going to happen is basically you can either say, well, what are the two ions? I'm going to do this. Here's the two ions. I put a slash after the metal. You wouldn't be able to leave this in a final answer, but just for notes here. There's an ion, here's the ion, and then here the Fe and the Cl. So the two metals, is probably the easiest way to think of it, are going to switch. So Na is going to be now with what? Cl. And Fe is with what? OH. And notice I didn't take the subscripts with them. Okay? This 3 and this 1, I just switched the elements. Didn't do subscripts yet because I have to figure out what the subscripts need to be, what the formulas are. And that's just as simple as that Na is a 1 plus, remember? Cl is a 1 minus. So I need one each of those two ions. So that's the formula already. Okay, on a quiz or homework, you'd erase those. The Fe, what charge was it? 3 plus. This 3 came from up there. Okay, the 3 here was crisscrossed from the iron. So this is Fe3 plus. And what's the charge on hydroxide? 1 minus. I'm going to put that in parentheses. It's polyatomic. So 1 minus, the 1 goes down to the iron, and then this 3 goes down with the hydroxide. So the 3 goes right there. And that's why I need the parentheses. If you didn't put the parentheses on this one, it would be wrong because it would be 3 hydrogens. Okay? So really watch out for that. And then we need to balance this. Okay? So I'm going to erase just a couple things here. Clean it up. So now we need to balance this. Might help to do this. There's hydroxide there, and there's hydroxide on the right side as well. So we can try to balance those first or last. I don't care. There's 3 hydroxides on the right side. How do we get 3 hydroxides with the sodium hydroxide? 3 after or 3 before? 3 before, because this formula is set. Now we change the sodium, though, to 3. So we need to multiply this by what? 3. Now we change the chlorine to 3. So now we need to multiply this by what? Nothing, because there's already 3 chlorines here. There's 1 iron, that's balanced. Good amount of trial and error with these. Have a good eraser. Don't be afraid to write things down. The worst thing you can do is sit there and look at it. Try to balance it in your head. You can always write stuff and just erase later. So this one, silver 1 nitrate, is mixed with sodium chloride. Pretty common reaction. Silver 1 nitrate is mixed with sodium chloride. So we're going to need to get some formulas here. And I'm just going to kind of work off to the sides and everything. So what's the symbol for silver? Ag, good. What's the charge on this silver? 1 plus, because of the 1, or the Roman numeral 1. So it's silver 1 plus. I need the charges to get the formula. It's an ionic compound, has metals and nonmetals. Nitrate, what's nitrate? NO3. Charge? 1 minus. So we got a 1 plus and a 1 minus. You just need 1 of each ion. So silver nitrate is AgNO3. Is mixed with. So plus. Sodium chloride. That one we've used a lot. Kind of know it off the top of our heads. It's NaCl. Okay. Arrow. This is definitely a double replacement again, because you have an ionic compound reacting with an ionic compound. Okay. And the 2 metals are going to switch. So Ag and Na, those are the 2 things, the double replacement things. So now Ag is going to be with, it's going to knock sodium out, it's going to be with Cl. Notice I'm not looking at the activity series for this. For now, you just assume it happens. Single replacement, you look at activity series. Plus the Na is with the NO3. Okay. The sodium chloride, I'm just going to write a note about that real quick. It was Na plus and Cl1 minus. You need 1 of each. All the charges are 1. If you do these little scribble notes off to the sides, Ag, you say, okay, I had that. That was 1 plus. Cl was 1 minus. I need 1 of each. Na was 1 plus. NO3 was 1 minus. I need 1 of each. So how do you balance this now? It's balanced. It's about as easy as it gets. Okay? It's already balanced as written. You don't have to do anything else to it. And then the 5th type of reaction, and the last general type for now, says combustion, and I'm saying combustion of a hydrocarbon in particular. All right. So combustion, I'll come back to this hydrocarbon in a bit here if I don't have any notes on it. So combustion simply means add oxygen. So add oxygen, and mathematically this symbol for add is a plus sign, so it's something plus oxygen. And remember, oxygen is going to be O2 because it's one of those diatomic molecules. So we're going to add O2. When you burn something, you combust it, it's adding oxygen. You need oxygen for combustion to occur. All right? So when I say combustion of a hydrocarbon, this is what a hydrocarbon is. A hydrocarbon is a compound with carbon and hydrogen in it for sure, and maybe there's some oxygen as well. And then, of course, that's going to react with oxygen gas, O2. So hydrocarbon, if you wanted to put it up here too, has carbon and hydrogen in it for sure, and maybe oxygen. Some of them will have oxygen for you guys for now. You've had a lot of combustion reactions on homeworks here and there. C6H12, things like that, reacting with oxygen. And now we're going to add to a little bit that we've had. We've already had this, and many of you know it and are aware of it and been talking about it, and it wasn't a reading guide first, but if it's something called complete combustion, it's efficient burning, in other words. It's doing what it's supposed to do. Then the products are going to be carbon dioxide and water, CO2 and water. Right now, your bodies are efficiently combusting sugars in foods. And you're producing CO2 and water. You're breathing out CO2 and water with every breath. Okay? It's complete combustion. So there's complete combustion, and then if it's not complete, what's it going to be called? Incomplete. Okay? So incomplete combustion is a type of combustion you don't want to have occur normally. The products are going to be CO and H2O. What's CO? The name of CO? Carbon monoxide. So that's when you have incomplete combustion in a car, it's not burning hot enough. Or a furnace, potentially, a heating furnace at home. You don't want that carbon monoxide produced because it's poisonous. So we'll do some examples now with this. So these are just some good general notes to have for potential multiple choice, the complete combustion and the incomplete combustion. I'm going to tell you which one on the problems now, okay? And if I don't, then you're going to assume something that I'll have in the notes right here. So an example, we're going to do the complete combustion of C6H12O6 plus O2. So again, I'm giving you the start of it. We're talking about it in notes, but let's say we weren't just talking about it in notes, this was in a homework. And you'd have to label, well, what type of reaction is this? And you'd say, oh, I'm adding oxygen. So it's a combustion. Okay, so this is a combust situation. And it doesn't have to be a hydrocarbon. It could be magnesium or anything for that matter, but a lot of people call those combinations. So this one, what are the products going to be? CO2 and water, because I'm saying complete. Okay, so CO2 and water, H2O. And we have all the elements, same elements on the right side and the left side of the arrow. It's just not balanced yet. So there's a trick I already taught you, and that trick is to leave what element for last? Oxygen. Always balance oxygen last in a combustion. It just makes life a lot easier. I would just start with the carbon. So we have 6 carbons on the left here. I'm going to try 6 on the right. I don't know if it's going to work, but I can always erase. 12 hydrogens on the left. So to get 12 hydrogens on the right, I need to multiply the water by what? 6. Now we can look at our oxygens. Okay? We have 6 here times 2. There's 12 oxygens right there. Just going to write little notes to myself. And then there's 6 times 1 oxygen. There's 6 more oxygens here. So that's a total of how many on the right? 18 oxygens on the right. Okay? We need to get 18 oxygens on the left here. I'm going to leave this for last again because we already have 6 right here. If I subtract off 6 from that 18, I'm going to be left with what? 12. I need 12 more oxygens. I need to multiply this by what? 6. And that one's done. Okay. The next one, I'm saying the incomplete combustion of CH4 plus O2. Methane gas. If you have a natural gas furnace at home, which if you're in town, there's a very good chance that it's a natural gas furnace. Could be electric, could be oil. Probably not propane. And the reason I'm guessing it's probably not propane is that's more out in the country and propane is more expensive. If you can get natural gas, you're probably going to go with natural gas. So CH4 plus O2, it is a combustion because we're adding oxygen. It's incomplete though, so what are the products? CO this time, carbon monoxide, and water vapor. Even in a car, there's combustion in the internal combustion engine. What do you see coming out of the tailpipe? In the winter, steam. In the summer, sometimes you see water pouring out as you're behind somebody. I always see it like by Perkins and Econo Foods and that, where you're at a little incline that people take off and water pours out of the exhaust pipe because they've been sitting there and it's condensing on the inside of the tailpipe, and that causes rust too. That's why short drives are not good for your exhaust system. Longer drives get it up to temperature and it's a vapor. So we need to balance this now. Leave the oxygen for last again. Go with carbon and hydrogen first. I'm seeing 1 carbon, 1 carbon, 4 hydrogens right here. So I'm going to try to get 4 hydrogens here by multiplying by what? 2. So now oxygens. I have 2 oxygens here, plus 1 more is 3 oxygens. That's going to be nearly impossible. It is impossible to get an even number here. Okay? So that's not working out. What do we try? Thought I just heard something. Double, yeah. If you get a case where there's odd number, double, so that you get even. So if I put a 2 here, there's 2 oxygens on the CO now. There's 2 oxygens on the water. That's a total of 4. Okay. But what just happened to my carbon? I doubled that. So I got to go back over here. I need to double that. But what did I just do to the hydrogen? Doubled that. So now there's 8 there. So what do I got to do here? Put a 4. I'm do that, and then I'll erase when I get sure here. So now everything except the oxygen. So I have 2 oxygens plus 4 oxygens is 6 oxygens on the right side. How do I get 6 here? 3. So combustion can be tricky sometimes, as you just saw with that one. And that one is done. And then the last thing here. If it doesn't say, if I don't tell you in a problem or somewhere else along the line, it doesn't say, assume it's complete combustion. Put the products as CO2 and water. Okay. If it doesn't say, assume it's complete, CO2 and water. And that's it.